So how do we solve for those maximums and minimums? Well, we can start with Fermat's theorem to give us some ideas. And this is, of course, this is due to Pierre Fermat, but there's a lot of theorems due to him. But this is what we're going to be using. And this is not news to you because we've been talking about this, right? The theorem says that if f has a local minimum or maximum at a particular point C, and the derivative exists, then the derivative is 0. So it has a horizontal tangent line, right? And we've been thinking about that, and we've been using that for quite some time. If I have something like this, right? I see all of those peaks and valleys. We've been thinking about the fact that at the top and the bottom, I can see that I have a horizontal tangent line. So at each of those points, the derivative is actually 0. So this is a good place to start to look for those kinds of points, right? Take the derivative, set it equal to 0, and solve for that. The thing you have to be careful with is it's not the end-all and be-all, because there's a couple of things we have to be careful of. It doesn't go the other way. Not all points that have horizontal tangents necessarily are a local min or max. And let's think of an example. What if I do y equals x cubed? That one flattens out and goes back up. If I take the derivative, I'll just call it f of x instead. If I take the derivative is 3x squared, and of course it is equal to 0 at x equals 0. But we can see this is not a maximum or minimum, even though it has that horizontal tangent. And I told you guys, actually, this is called a point of inflection, and we'll learn that later. Well, this is now. Later is now. So we have this horizontal tangent, but the function didn't go back down. It just kept looping up. All right? So just because the function, the derivative is 0 at a particular point, doesn't necessarily mean that it's a local maximum or a minimum. It just might be. Another kind of example that brings this out is our friend absolute value of x, right? Absolute value of x over all of r clearly has one minimum, and that's at x equals 0, right? But we know I can't take the derivative here because this derivative doesn't exist. But still, it's a minimum, right? So the question is, how we're going to figure out how to use this thing, how to use this theorem in an effective way so that we can, figure out what is and is not a maximum or minimum. Well, let me just give you a quick definition first. So what we're going to do for our definition here is that we're just going to call all these C's that we might want to think they might be a maximum or a minimum, we're going to call them critical numbers. So a critical number of a function f of x is a number C where either f primed of C is 0 or f primed of C doesn't exist. Okay? And so it turns out, and you can prove this pretty immediately because of Fermat's theorem, if you have a maximum or a minimum, a local max or a min, it's going to either be where the derivative is 0 or where the derivative doesn't exist. So there might be a point where the derivative doesn't exist, where it's not a local max or a min. There might be a critical point where, a point where the derivative is 0, where it doesn't exist, but all the maxes and mins will be critical points. Okay? All local max and mins will be at critical points. So it seems to make sense that if we want to find all the critical points, we can find all the critical points, and then we can check to see which ones are the mins and which ones are the maxes. Right? Check which is the max and which is the min. Okay. Now, there's a subtle point, right? We can find all the local maxes and mins, but to find an absolute max or a min, we want to find the biggest of all of them, right? So we'll have to check them all, and we also have to check the endpoints, because we saw, so we can try to find local maxes and mins this way. If we want to try to find absolute maxes and mins, we also have to check the endpoints. So let me write this up. This is, again, related to the extreme value theorem. So to just make it a little bit clearer. In this section, which is 4.1, we're pretty much going to use these ideas of Ferma's theorem and looking for the critical numbers and using the closed interval test to find the absolute max and the absolute min of a function, a continuous function on a closed interval. So that's actually what we're going to do. Now, we'll also find information here, that we might have some numbers which are local maxes and local mins that are, other ones that may not be the biggest or the smallest. We're not really going to do anything with that particular information in this section, but in the section 4.3, which again is this week, so this is what we're doing this week. We'll be also using additional information in order to figure out which is a min and which is a max and where it is on the graph and how to start graphing functions with this information. So it's all going to kind of go together. So absolute max and min, but then also we're going to be doing some local max and min and graphing functions, and how derivatives essentially affect the shape of the graph. Okay, so for this section 4.1, the big result really is the closed interval test, which is how we are going to find the absolute max and the absolute min of the function on the interval, right? So to find the absolute max and min of a continuous function on a closed interval AB. Okay. First thing you're going to do is you're going to find all of the critical points. Of course, we really only care about the ones on the interval, right? So find all critical points of f on the interval, right? And then we're going to make a little table of it. You're going to find the values of f at the critical points. And then you're also going to find the values of f at the endpoints of the interval. And then you're just going to look at which is the biggest and which is the smallest? Okay, so when we have them all listed on a table, we're just going to look, and it's going to be the largest of these largest of the y values, right? F of whatever is the maximum as the absolute max. The smallest is the absolute min. Okay, so now I'm going to do some exercises, some examples, but we'll put them in a different video.